quickly just share the video. One second. There's no button for the video, but okay, one sec.
Hi, my name is...
Sorry, the interface is a little bit different from when we practiced it before, so I just gotta... Oh God, now it's glitching out. I can't see my own screen. Okay, sorry, I gotta try this one more time.
Yes, don't worry. We are still 1 minute ahead, so no problem.
Okay. Let me know if you can't hear it or anything like that. I'll just start playing now.
Hi, my name is Sina Khajehabdollahi, and I'm a PhD student here in the University of Tübingen in the lab of Anna Levina. I'm interested in self-organizing systems, open-ended evolution, and the intersections between machine learning and biological systems.
Hi, my name is Giannakakis. I'm also a student in Tübingen in the same group as Sina, and I work on plasticity and optimality in biological neural networks. I'm interested in how computation happens in biological systems, and possible applications of insights from computational neuroscience in designing artificial neural networks. Today, we are presenting our work on how a simple
Try to start it again, because otherwise we hear you doubled if I don't mute you. But it should work. No, it doesn't work. Okay. Please activate again your audio. I think we cannot do better. It's still not active. Yeah, I'm sorry. Yeah. Let's leave it like this.
Can you hear me now?
Yeah, not super well, but I tried to solve it, but let's leave it like this as it was before, sorry.
Okay.
biological plasticity rule can boost the ability of a reservoir computing model to self-organize and adapt to changing inputs.
Reservoir computing is a computational framework that uses a recurrent, non-trainable network to project inputs to higher dimensional spaces. As opposed to traditional neural networks, which usually require end-to-end training, that can be very task-specific and computationally expensive, reservoirs employ a static recurrent network which does the bulk of information processing and is interpreted by a simple linear readout layer that can be easily trained via linear regression. A good reservoir needs to extract all the useful information from an input so that it can be best interpreted by the readout layer. Furthermore, a reservoir need not be task-specific, as one can train multiple different readout layers simultaneously on different tasks. The problem, of course, is to find such an appropriate reservoir, which may require a lot of fine-tuning. What we try to show here is that using biological neuro-inspired plasticity can make the reservoir self-tune and adapt to different inputs and tasks.
For our reservoir, we use a recurrent network of Wilson-Cowan oscillators. A Wilson-Cowan oscillator is a model developed in the 1960s by Hugh Wilson and Jack Cowan. It aims to represent the dynamics of an interacting population of inhibitory and excitatory neurons that are driven by external input. Thus, a Wilson-Cowan node consists of two interacting units representing an excitatory and inhibitory population of neurons. Each unit receives delayed input from itself and the other unit, as well as an external stimulus. The inhibitory nodes give negative outputs, and the excitatory nodes give positive outputs. The summed weighted inputs each node receives pass through a nonlinearity, and the resulting system can display very complicated dynamics, which accurately represent the dynamics of cortical networks. In our setting, we use a number of such nodes to construct a recurrent network by sparsely connecting the excitatory units of each node. We selected this model because recent studies have shown that such networks can employ a local inhibitory plasticity rule to regulate global network dynamics, and we wanted to explore whether these properties can be used in the context of machine learning. When we look at experimental studies of the brain, we observe that the connectivity of biological neural networks is constantly changing in time, and there seems to be a variety of rules describing how these adaptations occur. The most well-studied type of plasticity is Hebbian plasticity, which strengthens connections between correlated neurons and weakens connections between uncorrelated neurons. But multiple other types of plasticity have been observed as well. Neuronal plasticity has a variety of roles, including learning and homeostasis, and it has been shown that the combination of different forms of plasticity, acting on varied timescales, allow networks to self-organize in a wide range of circumstances. This ability to self-organize is especially attractive when designing reservoirs, and it has been shown to successfully optimize performance in a variety of tasks. For example, Andrea Lazar, presenting in 2009 a self-organizing neural network which uses a combination of plasticity rules to optimize network dynamics for learning. Moreover, a recent preprint by Lloyd showed that synaptic plasticity can improve the ability of a network to learn even if it is only exposed to unstructured input. Finally, Hebbian-like plasticity has been shown to optimize network performance in more complicated tasks, such as reinforcement learning problems, as was shown by Elias Naharo. In our project, we decided to examine the self-organizing capabilities of a local inhibitory plasticity rule, which has already been demonstrated to impact the dynamics of networks of Wilson-Cowan oscillators. Specifically, we employ a variation of the plasticity rule described by Vogels, which regulates inhibitory connection strength in order to keep the postsynaptic activity close to a target rate. Here is the simple equation that describes this plasticity rule, where the second term on the right is a function of the difference between the postsynaptic excitatory activity E and a target rate ρ0. If the excitatory activity is above the target, the inhibitory connection is strengthened, which drives the activity down towards the target rate. If, on the other hand, the activity is below the target, the term becomes negative, leading to a decrease in inhibition, which in turn increases the postsynaptic activity. In the context of the Wilson-Cowan network, this rule is interesting because it is only active locally between the two units of each node, but it has been shown to shape global dynamics. It is this property of a local rule whose effects can be easily understood, giving rise to global effects, that makes this plasticity rule particularly interesting for us.
In our model, our reservoir is a network of sparsely connected plastic Wilson-Cowan oscillators. Our aim is to examine whether allowing a network to self-tune via plasticity makes it more robust or more generalizable. To this end, we define a demixing task to test our reservoir's capabilities. The reservoir is fed a mixed signal of two sinusoids of random frequency and amplitude and is expected to output the higher frequency signal of the two. It is essentially a bandpass filter task, where the bandpass has to be somewhat adaptive. The networks we use all have 300 nodes and are sparsely connected with a 5% connection probability. We use 80% of the neurons as read-in neurons and 95% of the neurons as read-out. In the end, the network performs well on the task and manages to reconstruct the target sequence reasonably accurately. Our aim is to examine how plasticity can help the network self-organize and become more robust. At first, we observe that without plasticity, the network's performance heavily depends on the distribution of internode weights. As you can see in these images, different distributions of weights lead to different dynamics and behaviors. As a baseline, we draw our weights from a log normal distribution with a specific mean and variance that we observe do well on the task. We then examined what happens if we draw the weights from different distributions with different mu's and sigmas. Here we observe that without plasticity, the network can only perform well for a narrow range of parameters. On the contrary, if we allow a brief pre-tuning period with the plasticity rule active before the training begins, the network becomes virtually connectivity agnostic and performs equally well for a very broad range of parameters. Nodes to a stable point, with either constant high or low activity. Such activity is not interpretable by the readout layer, which has to solve the task with the information that can be extracted from the few remaining oscillating nodes. On the other hand, if we include the tuning step, the plasticity rule adjusts the inhibitory weights so that the activity of the node is near the target rate. In that way, the node is pushed towards an oscillating state around the target rate, which makes it much more sensitive to input changes and thus more interpretable by the readout. This means that tuning with the simple plasticity rule that we use allows us to basically randomly initialize the reservoir without spending large amounts of time to find the exact initialization for the task at hand. Additionally, we examine if the retuning mechanism can help the network adapt to varying input. The idea behind this is that backprop training is expensive while plasticity tuning is cheap, and therefore, it makes sense to use a plasticity mechanism that shortens training time. To test this idea, we use the dataset from the previous experiment, but in this case, instead of changing the reservoir's connectivity, we scale the input currents the reservoir receives. Specifically, we define a range of additive and multiplicative scaling factors that transform the mean and amplitude of the input, and then we train the reservoir for these input currents until the loss converges. Then, using a different additive and multiplicative factor, we rescale the input each reservoir receives and retrain for a fraction of the original training time. We then compare the performance of the reservoir with the original input before retraining, and the performance with the new rescaled input after retraining. In general, we observe that the more similar the current pre- and post-rescalings are, the better the reservoir will perform post-rescaling, as expected. If we include a brief plasticity tuning step between the rescaling and second training phases, we observe that the reservoir is much more adaptable and performs near optimally, even for significant transformations of the input. As in the previous experiment, this happens because the inhibition is adjusted to keep most nodes oscillating under the changed input, unlike the case where there is no retuning, where many previously oscillating nodes will now move to stable states and will therefore no longer be interpretable by the trained readout weights. This shows that a simple, computationally cheap plasticity rule can make a complicated reservoir much more adaptable and reduce its required training time for perturbed inputs. In short, we show in our experiments that simple biologically inspired mechanisms can endow a reservoir with self-organizing capabilities to adapt to a broader range of internal properties and inputs. We believe that these principles might be necessary for designing generalizable learning systems, and we hope that our results motivate more studies in this direction. Thank you all for watching, and we would also like to thank our colleagues and our funding sources for making this research possible.
Thank you. So, do we have any questions? Yeah. Okay, please.
Hi.
Hey.
Sina. I have a question. Do you have an intuition why on this second to last slide or so you showed that when you scaled the input, right, but you actually, for the case where B was 0, the performance was relatively bad with plasticity. Do you have an intuition why this is happening?
Yeah, so can you hear me?
Yes.
Yeah, so if we scale, so if we have additive factor of 0 and multiplicative factor of 1, we practically don't scale the input, so nothing changes. So if we have trained and then add plasticity after training, things will get worse because the reservoir changes. So when the input it remains the same, so there is nothing to adapt to.
I see.
While in the rest of the cases, the input changes, so the reservoir adapts to the new input with plasticity. But if you don't have any change, you don't need retuning.
But I would expect that the retuning plus retuning the readout wouldn't really change anything, would it?
It would, because the rule does change a bit the in network dynamics. So if it's performing well and if it's performing optimally at this point, and then you make some change, it would take some time to adapt. Like there is nothing to bring it back to because it's already oscillating.
Cool. Thanks.
Any other question?
Well, if there's none, I have another one. We have some time, right? So
Yeah, go on, please.
You use quite a large fraction of the units as a readout. Did you try with a much smaller fraction, or what was the reason for using such a large number?
Yeah, so originally we experimented quite a bit with it, although in the latest iterations we kind of stuck with that fraction. It is a large fraction, so ideally in future experiments we're going to slowly wean that away. to as low as we can go. So I think our plan is to document exactly how changing the sparsity, for example, or changing the read-in, readout percentages affects this entire thing. This was obviously a generous sort of broadcasting of the inputs and outputs. And we found that making it less it kind of broke the reservoir, so it couldn't really solve the task in the way that we wanted to test the things that we wanted to test. But the idea definitely is to bring these percentages down to like the minimal value and document how it does so and what it takes to get there. At the moment, the signals don't propagate well enough if the network is too sparse or if the read-in is too small. So if only a small percentage of the neurons are getting it, yeah, we have some problems gaining signal. So because we're playing with inhibitory plasticity, we can attenuate stuff, but having gain requires, I think, something Hebbian or some STDP-like rule. And well, we've been experimenting with that, but it's very slow to run computationally. So it's we don't have results for this particular project at the moment, anyway.
Thanks.
Hi, hi. Thanks for the presentation. I am a bit curious. Why did you choose this bandpass filtering task, and how do you expect the results to generalize to other tasks, or if you have tried, to apply the same setup to other learning tasks?
So I would say the motivation is that the idea of using a reservoir is that you have some kind of live signal coming in. I think like this is the context of reservoirs that I was at least kind of exposed to, and I think is an interesting one where you have some kind of substrate or maybe a neuromorphic chip or whatever, and there's live information flowing in. And so we wanted something time series-esque or a sequence of some kind. And there are a bunch of sort of benchmark tasks that people have used, but some of them were more or less interesting for us. So we haven't like we have a list of tasks that we eventually want to apply the same experiment for, but this was one task that we thought was a reasonable difficulty and one we could code from scratch, and in which the baseline would be kind of obvious what it should be. So it was mostly to make a benchmark for ourselves. And also we found some other papers that did similar tasks, and we thought, okay, this is probably a reasonable task for us to test our reservoir on and just to see how it behaves. And then our future projects in this vein are related to like reinforcement learning and gym environments, so or like games in general. So the intention is to take it to more generalized tasks. And yeah, how it generalizes to other tasks, that's something we will see. So I think the idea is that a priori, a network that hasn't been trained or anything or tuned or anything, it doesn't know what kind of inputs it should expect, and how this propagates through the network, it also doesn't know. So it could have vanishing signals or exploding signals. And we think that this is kind of solving this kind of problem with this sort of homeostatic inhibition. To generalize to much larger sets of or families of problems, I think we need different types of plasticity in combination. And again, specifically, I think something in the STDP family is what we're missing. So that's how we expected it might generalize, is in combination.
Any other question?
Yeah, I have another one. If there's no more. So you suggested that do you think the system is working well because the plasticity allows your reservoir to be to start from a regime which is not saturated or inactive and just in this middle part where it's sensitive. So do you think so that this could be like something that could generalize to other systems, or if you could have a simplest reservoir that just tries to find this this kind of intermediate sensitive regimes aside from your system? Yeah.
So it really depends on the type of reservoir and what types of plasticity can be applied. But any recurrent system which is time continuous will have better and worse states for the readout layer to interpret it. So the idea is that for any such complicated system, there could be some self-organizing principles, some self-organizing rules that push it towards that state. So the idea is you give the input and the reservoir projects it to this interpretable space. And the idea of the plasticity self-organization is to kind of have a bigger range of inputs that can be projected in that space. So in theory, yeah, different reservoirs that can also be at better or worse states for interpretation should be able to be organized by plasticity rules. Now, the rule that we use is kind of specific for the system, for the specific connectivity that we're using, the Wilson-Cowan thing with like local inhibition for its node. But it could work for different things. So if we have both excitatory and inhibitory nodes, even if they're not in a Wilson-Cowan connectivity, there should still be some benefit, probably. And if we have on excitatory nodes, a classic recurrent network, then probably something Hebbian that gives activity like with maximizing correlations, or something homeostatic could still make things better, presumably.
And just to add to that too, so I have a couple parallel projects that they're not at a point yet where I'm like, they're not A-Life ready or anything, but so I've been playing around with some cellular automata stuff, and some of the problems that you face in that are things dying, for example, the entire network dying, or the model itself is maybe a bad model, because I'm messing around with the architectures as well in my neural cellular automata. And so I've been toying with the idea of introducing plasticity in the update rule for the neural network for the cellular automata as well. And there were talks, I think Monday, on using cellular automata as reservoirs. And so I think in principle, this idea has some parallels with the whole ideas of like criticality, and it's pretty substrate free, I think. So in principle, I think it's a universal thing that somebody wants, is that you don't want it to be fully saturated or dead. So there's a sweet spot in between, and finding it in a sort of self-organized way is the dream, I guess, and doing that in a consistent way, in a principled way. So yes, I think these experiments and these results should extend to other types of reservoirs or other types of models. So I hope they are not too specific to our model, because that is not the intention for the research.
Perfect, thank you. So I think that to stay in what planned and in the schedule given me, we are closing here this session of talks, and we will be back in this room instead at 12:30, instead with the special session of hybrid life. I stop the recording and I will close this room. See you later.